So our thermometer is not calibrated, but we do for sure know that we are putting heat energy into this, and our temperature over here, it is not changing. It's not changing at all. So this is a very, very important thing we need to talk about. This is where we get into latent heat, or what we call hidden heat. So changing the temperature of the water from 32 all the way to 212, that was sensible heat. The catch is, now we're at 212 degrees Fahrenheit, and we're still at 212 degrees Fahrenheit. But what did change? If we take a look, you may not have noticed, but we actually have a change right here. We started out with 1 pound of water. If you notice, now we're down to 6 ounces of water. So we have changed something, and the key is that we have changed state. We took this water from being the liquid form, and now we're changing it to a vapor form. It's actually going into the air. It's changing state from a liquid to a vapor. And it takes a whole lot more BTUs to make a substance change state from a liquid to a vapor than it does to simply change in temperature. So let's look at a few more little things that we need to know here. If we were to take this water from 212 and keep it at 212 steam, I don't have that facility to make that happen because we have other things in the air. We have oxygen, nitrogen. If you see this steam that you see here is actually the water recondensing and mixing back with the air. So this water here is not even at 212. But staying at 212, how much energy would it take to make all of this water change state? How much BTU would it take? And that's what's interesting. So before we get there, let's talk a little bit about sensible heat. If we wanted to define sensible heat, which is typical in most places, most schools require you to know the definition, and the definition. So let's add a little definition here for sensible heat. Sensible heat. And it's pretty simple. Sensible heat is heat we can sense. It's heat that we can sense. And if we want the formal definition, it causes a change in temperature. Without a change in state. A change in temperature without a change in state. So when we talked about our BTU formula, we went from, we ended up at 212 degrees Fahrenheit, and we started at 32 degrees Fahrenheit. And if we want to do the math on that, most books can do this ahead, but if you can't do math, it's okay. Pull out your calculator, put the numbers in, and you'll see it ends up at 180. So we had a temperature change of 180 degrees Fahrenheit. 212 minus 32 is 180. We had 1 pound of water. So it took 180 BTUs. So it took 180 BTUs to change 1 pound of water 180 degrees. That's 1 BTU. That's all sensible heat. But just now we got to see us adding more heat energy into this, and we still do not have a change in temperature. So this brings us to our next little point we're going to have. Our next little vocabulary word. So this vocabulary word, we're going to have latent heat. Now my spelling is atrocious, and so is my handwriting. I'm writing this down so that you write this down with me. I already know this stuff. It doesn't help for me to write this down. You need to be the one writing this down. So latent heat. Latent is Latin for hidden. So latent, hidden, it's hidden heat. So it's hidden heat. So we're going to write this down. Hidden heat. Hidden heat. So let's define what hidden heat is. It actually has a definition. Maybe this definition will help you understand what it is. So latent heat, hidden heat. It's going to be a change of state without a change in temperature. A change of state. So what's happening right now? Is this latent heat or sensible heat? The water is changing state from a liquid form to a vapor form out in the air. It's changing, it's physically changing state from a liquid to a vapor. But the temperature is still at 212. So how much BTU would it take to make this entire pound of water change? Let's see. If we have water at 212 degrees Fahrenheit, and we want to keep it at 212 degrees Fahrenheit, vapor, so I'm going to write liquid, liquid to vapor. How many BTUs do you think it would take to change it? It took 180 from 32 to 212. What about 212 to 212? Liquid to vapor. Come on, give me a number. Guess. Is that your final answer? Are you sure that's what it's going to be? Are you 100% positive? Let's look and see what that number would be. That number, drum roll please, that number is going to be 970 BTUs of heat energy. It takes 972 BTUs of heat energy. I have to put into this water 970 BTUs of heat energy. And it will make it change state from 212 liquid to 212 vapor. That is latent heat. That's latent heat, 970 BTUs. Now, scientists, they've done all the calculations. They've calculated this. They've taken the containers. They know exactly how much heat you're going to have electricity. They've put those heat energies in there. This is sloppy. We're losing heat in the sides and heat everywhere. But you can actually calculate that. And the scientists calculated, they found out at sea level, 970 BTUs heat energy to boil away 1 pound of water. You can see here, we're down to, our scale shut off. We're going to power it back up. We're down to less than 5 ounces. So we're physically losing the water that's in this container. It's going to a vapor form. It's changing state from liquid to vapor. To get rid of all of it, it's going to take 970 BTUs. I think that's absolutely amazing. 970 BTUs. I need you to have some appreciation for that. Let's put it into context. We talked about having a container of water. Let's put this a little bit of context. Let's say that this is at 32 degrees. It's all liquid. There's no solid. All liquid, 32 degrees. And I'm going to reach through the screen and I'm going to pour this entire 1 pound on you at 32 degrees. Imagine how that would feel. Think about your response. You would not be happy. You would be, oh my gosh, 32 degree water, maybe even put you in shock. It's a tremendous amount. Now it's heat this up to 212. It's not yet boiling, but it's right at 212. And I was to then reach to the screen and pour this on top of you, this entire pound. Would that be a significant difference between 32 degrees and then all the way up to 212 degrees? Would that be shocking? Yes, but that's only 180 BTUs difference. 180 has that much of an effect. Now let's think about it this way. 970 BTUs. That's powerful. It's huge. It's incredible. 970 BTUs of heat energy is tremendous. It's much, much more powerful than this 180. So I need you to understand that latent heat, hidden heat, is much, much more powerful. It absorbs so much more heat energy than sensible heat. Look at how much energy. 970. We didn't even change in temperature. Changing a state is huge, it's powerful. You've got to understand that. These definitions are good to know, have them down, understand it, but what I really need you to have right now is the appreciation for that change of state. 970 BTUs to change water from liquid to a vapor. If I have water that's in vapor form and I want to take it back to a liquid, guess how many BTUs I have to take out of that vapor? I have to take out 970. I have to pull 970 BTUs out of the air to make that water condense from a vapor back into a liquid for 1 pound. It's a tremendous, tremendous, tremendous amount of heat energy. Let's also think about this. You're in the summertime and you have a drink of choice instead of a metal can. Well, metal transfers heat very, very quickly. But also we have to talk about dew point temperature. We'll get to that a little bit later, but the temperature is below dew point. The moisture in the air condenses, changes state from a vapor to a liquid on the side of that can. As that condensation happens, it doesn't just leave stains on your wood cabinet that your mom complains about. No, it's actually putting 970 BTUs of heat energy into that drink. 970 BTUs of heat energy. That's that's change of state. Now, ideally, you're not condensing an entire pound of water, but the difference between heat going into your glass, just temperature change, versus the condensation forming in that glass is tremendous. This is why they build those little insulation devices, people call it a koozie. You put over it and it slows the heat transfer down just enough to prevent condensation. You ever gone into a very popular drink store and they have the drinks in the styrofoam glasses? They very, very seldom have condensation. That condensation prevents that heat transfer from a vapor to a liquid. It slows the heat going down into your drink. That condensation is putting way more heat into your drink. Also, this is important because not only does the air conditioner cool the air, its job is also to pull the moisture out of the air. It takes 970 B2s for every 1 pound of moisture that comes out of the air. You're going to have an inside evaporator coil, and under that coil is going to be a drain pan. That drain pan is for the moisture you're physically taking out of the air. 970 B2s for every 1 pound of water that drains out. Feels like, okay, well, that's something. Think about a gallon of water. How much does a gallon of water weigh? It weighs over 8 pounds, 8.3 something. I can't remember off the top of my head. Over 8 pounds for a gallon of water. So what's 8 pounds times 970? Let's look at that. Let's just do a quick little math. 8 times 970. To dehumidify, to pull 1 gallon of water out of the air, it's going to take at least 7,700. Now, there's much more math. You could get it much more ideal. But it's pulling a tremendous amount of B2 heat energy just to pull the moisture out of the air. In the wintertime, you live in a house someplace and you run the heat, the air is getting dry, you literally put moisture back into the air. Here we're putting moisture into the air. It's going to take 970 B2s of heat energy to make this moisture go into the air. To pull moisture out of the air, 970 B2s of energy per every 1 pound. So that change of state is extremely important. Latent heat, change of state.